At the most fundamental level, rockets are just precision-engineered Newton's third law machines, throwing exhaust backward, which in return throws the rocket forward. What does this mean practically speaking, and how is this high-speed exhaust generated? If all that rockets need to do to achieve orbit is throw gas backwards, why do they bother to light it on fire? Isn't there a safer option than building a giant explosive flamethrower? In the previous video, we discussed a very simple third law machine in the form of a canoe filled with bowling balls. As the bowling balls were thrown from the back of the canoe, they pushed it forward toward the lakeshore. The harder the balls were thrown, the faster the canoe moved. The reason for this is momentum, or the product of an object's mass and its velocity. The more momentum the bowling ball has, the more momentum it imparts to the canoe via Newton's third law. When constructing a rocket, engineers obviously do not use bowling balls. Instead, they use super hot gas molecules. Why is this the right choice? To find an answer, let's think about the molecules of a gas. Unlike a solid or a liquid, all of the molecules of a gas are free to bounce around the space that contains them. If we put a gas, say for example oxygen, into a bottle, the molecules will float around, periodically bouncing off of the inner walls. Every time an oxygen molecule bounces off of the wall of its container, it pushes on the container walls. The more molecules of oxygen are in the bottle, the more frequently they bounce off of the walls, and as a consequence, the more force the gas exerts on the container. We call this force pressure. As long as the oxygen stays in the bottle, nothing apparent happens from the outside, no matter how many molecules we cram into it. This is because, although the oxygen might be exerting enormous force on the inner walls, molecules are bouncing off of each of the inner walls with equal frequency, and their pushes all cancel each other out. Imagine, however, that we poke a hole in the bottle, or that it bursts. Suddenly, there is one wall of the bottle where it is less likely for the molecules to bounce and more likely for them to escape. This means that there is a stream of oxygen molecules pouring out of the hole and a net force on the opposite internal wall of the bottle. Because of Newton's third law, the whole bottle is pushed in the opposite direction of the stream of oxygen molecules. A rocket is just a bottle with gas streaming out of a hole in one end. However, simply filling a rocket with high-pressure gas and poking a hole in one side is not a practical way to accelerate the rocket to orbital speeds. Even if the gas is under very high pressure, the escaping gas will simply not push the rocket fast enough for it to reach orbit. How do we solve this problem? Remember our previous discussion of bowling balls and momentum. The faster an object moves, the more momentum it has, and the more momentum it imparts via Newton's third law. Clearly, therefore, we need some super fast-moving gas in order to push our rocket to orbit. The solution is combustion. You may have once heard that the temperature of a substance is just the measure of the average kinetic energy of its molecules. What this means is that on average, the hotter a substance, the faster its molecules move and the more momentum they have. Consequently, the hotter the gas when it escapes the rocket, the more energy it has to push the rocket. Imagine now that we add a bunch of hydrogen molecules to our oxygen bottle. If we ignite them before allowing them to escape, they will burn, rapidly recombining to form water vapor and a ton of excess energy in the form of heat. This heat will accelerate the exhaust molecules to somewhere in the neighborhood of 3,000 meters per second, which is fast enough to travel from New York to Tokyo in an hour. At this speed, trillions and trillions of tiny gas molecules have enough momentum to push even a multi-ton rocket into orbit.